1-hour speaker today, Julius Kaplonov, also like Danila from Kiel University, and he will tell us about his recent work on dynamics of a thin elastic layer lying in a Winkler foundation. Over to you, Julius.
Yeah, thank you very much, Kirill, for your introduction. In fact, I'm speaking from Germany. It's about 11 p.m. in Aachen. So in case I will fall asleep, yeah, please don't hesitate to wake me up. But I'll do my best nevertheless. Here you can see the plan of my talk. I'll begin with a brief introduction and motivation. Then I'll formulate the problem, starting with the asymptotic scaling, typical for a layer supported by an elastic foundation. I'll derive then asymptotically both leading order and refined order theory, starting from the exact boundary value problem in linear elasticity. Then later on, I'll demonstrate the associated dispersion relation and analyze it slightly. The final part of the talk, it's about a near cutoff degeneration of the basic, of the classical asymptotic behavior, and I'll derive leading order equation governing this degenerated case and show that this degenerated set of equation describes the so-called veering point of the dispersion curves corresponding to bending and extension waves. So here you can see a very popular traditional two-dimensional engineering model for a Kirchhoff plate supported by a Winkler foundation. Okay, here W is a transverse displacement. Delta is Laplacian, but it's a two-dimensional Laplacian specified in the tangential variables on the mid-plane of this plate. Well, D is the so-called stiffness of the plate, H it's half thickness, rho it's mass density, and the last term corresponds to the response of the Winkler elastic foundation. Theta is the coefficient characterizing this foundation, and in the right-hand side there is a prescribed transverse load P. It's a usual forcing term. This equation found really numerous applications in soil structure and fluid structure interaction problems. It wouldn't be wrong to say that over 1 million publications were somehow based on this engineering model. And I am not exaggerating. So, but still, as an applied mathematician, I strongly dislike the state of art. There is no proper mathematical justification of this model. Starting from the original 3D boundary value problem, which will involve the transverse variable across the thickness, and also will be based on mixed boundary condition along the low face of the layer. The low face of the layer. Usually, usually by a strange reason, engineers deal with not mixed, but Nyman type boundary condition at the low phase, treating the last term in the left-hand side at a certain prescribed load, like P. So forgetting of the mixed boundary condition and using the Newman results, which I strongly dislike, and also some experience in wave propagation hints that this equation will govern a cutoff frequency for which the squared Laplacian should be gone, and in the time harmonic regime we will have a certain frequency for which two last terms in the left-hand side compensate each other. So the asymptotic regime should be amended. It's a different one. Here you can see this picture. Yeah, I call it Winkler Foundation, but some Russian patriots may claim that it's a Winkler Fuss Foundation. Nicholas Fuss was an earlier student in St. Petersburg. I believe he was also of Swiss origin, and he published a similar paper as Winkler about the same time, but he published it in Russian, I'm afraid, and it has been noted for a while. Okay, but mostly it's known as a Winkler Foundation, giving a nice, simpler model, well, containing only a certain experimental coefficient theta. Okay, I will be cheating from the very beginning. As usual, I am too lazy to consider a full 3D problem. I will start with a 2D plane problem, which still contains the transverse variable alpha 2, but it's a plane problem with the only one tangential coordinate alpha 1. We have wave equation of motion and linear elasticity. Sigma denote stresses, which are first order differential operators of the displacement V1 and V2. V2 is the transverse displacement, the vertical one, while V1 stays for tangential horizontal displacements. There are material constants here. E is the Young modulus, and nu is the Poisson ratio. And T, of course, stays for time, for a time variable. So our aim to get rid of the transverse differentiation of this system and reduce this 2D problem to a 1D problem for a beam, but of course it's not the whole story. The boundary conditions on the faces are very crucial. We consider that tangential displacement equals 0 along both faces. The normal displacement equals the prescribed force P, prescribed stress P along the upper face. And what's crucial, but still very natural, the latter displacement equals theta times V2, corresponding to the effect of the Winkler foundation along the low faces. And as I said, theta is the Winkler constant. What is the engineering approach? They don't like the third mixed boundary conditions, because all the history, including the history of asymptotic integration in plates, is mainly restricted to the Newman boundary conditions. And their philosophy is to denote in the last boundary condition the product eta times V2 by a certain quantity Q, which treated as the prescribed force or stress P, not as a certain function of an unknown displacement V2, but they are forgetting about that and thinking that this product can be treated as a given quantity, a force, another forcing tool. And well, it makes me a bit nervous, the mathematical background under this simplification. It's very shaky. And I'll consider, of course, from the very beginning, the mixed problem along the faces. So another assumption, mathematical assumption, coming from physics, which fully ignored by the engineering community. They say very little or nothing about the fact that the foundation should be relatively soft with respect to the layer itself, and G capital, which is a certain ratio of stiffnesses, theta over E, but H also comes into the game upstairs. This ratio should be much less than unity. Otherwise, not assuming that, you would never have bending vibration of interest. The beam should bend on the foundation, and foundation shouldn't stop the bending process. In all the application, especially the original one in civil engineering, it's assumed. And when some practitioners take G relatively large, they should have absolutely different models. They would never arrive to the Kirchhoff model. It's important point, and from the very beginning, I am assuming that this ratio is a small parameter. So what I'm doing, taking a mixed boundary value problem and assuming the existence of a specific small parameter. Next, I'm considering long wave vibration and scale the original variables this way. This is natural scaling for the thickness variable, just normalizing it by half thickness, but also for the sake of simplicity, in order to avoid two parametric analysis, we are defining in a tricky way through the small parameter G, we are defining a typical wavelength, which is much greater than the thickness in case when the Winkler foundation is soft enough. So it's another a bit of trick, but we'll now have basically a single small parameter G connecting it with typical wavelength lambda. So also using this small parameter, we are normalizing stresses and displacement, and also the external force, well, according to the classical idea of a bending type of motion, which was also typical for a free layer, not a layer on a foundation, but in a free layer, we would like to have the same asymptotic behavior. The forthcoming calculation shows that these assumptions is fully justified, and well, we are working within that framework. So we are substituting the scaled variables and unknowns into the equations of motion. All the start quantities are assumed to be of order of unity. Well, and the differentiation along the scale variables do not change the asymptotic order. Here, the parameter epsilon, which is a nicer small parameter than G, the original one, you can see here the relation between them. This parameter comes explicitly here, and we can now integrate the system of ordinary differential equations in the transverse scale variable zeta across the thickness, using the fact that epsilon is small. Here you can see boundary conditions. So all the unknown quantities are thought as asymptotic series in epsilon squared. It's a routine now. It was done many times in mechanics of thin elastic bodies. Originated to Goldenweiser. In dynamics, it was probably developed by my own mostly. Nevertheless, I am omitting the technicalities, and here you can see a scaled still, but leading order approximation. For the leading order, again, transverse displacement V2. We have a fourth order equation with a dynamic term corresponding to a Kirchhoff plate or to a beam in 1D case, yeah, and the second term on the left-hand side corresponds to the effect of the foundation. It appears that at leading order, a rough engineering setup can be fully asymptotically justified to a certain extent. I'll clarify why to a certain extent in a few minutes. But the classical model is derived from 2D elasticity, in this case at leading order. So no harm to produce to the next order. And now I presented the equation in original variables, and you can see the corrections with the factor h squared in all three brackets. You can see that we should refine, firstly, the inertial term, secondly, the Winkler term also we should refine, and this refinement on the Winkler term contains second derivative. Well, we may say that it will be not more Winkler, but already Pasternak foundation with a derivative into here, but Pasternak did it as a leading order one, but here you can see that this term, the second order derivative, is still correction. It will be mess in ad hoc theories. It's even difficult to compare the results with them. And finally, we should also slightly correct the applied load. By all means, this equation cannot be derived starting from any engineering assumptions or physical assumptions. It's virtually impossible, but in this case, it's hardly reasonable to blame non-mathematical community because it's tough. If the leading order equation can be somehow predicted without a proper derivation, higher order assumptions are usually outside the area of intuitive. Yes, please.
Sorry. What happens if P is has I mean, if you take say a sequence of forces whose second derivative increases, right? What if you take and eventually if you take P that is not twice differentiable?
It requires separate consideration. You will have boundary layer near the points where P is not twice differential. Yeah, here it's assumed, of course, that it's twice differential.
Right.
So, yeah, but you will have boundary layers. It's a more difficult problem, a specific one. Somebody did it definitely, not in this setup, but for sphere, I believe. Yeah.
Right, and also this effective equation, this is like
yes.
an equation, right? For the original problem. Would you have estimates on the error in terms of h?
Oh yeah, h to the 4. H to the 4.
Right. Okay. But it would get worse. I mean, in what norm, in what function space is this estimate? In what norm? Function norm?
It's generally in L2, but I'm afraid I cannot produce rigorous results with norm estimate. It's slightly not mine specialist.
So it's an L2, but in terms of the L2 norm of P, or what norm? I mean, it has to be higher than L2 in P for P. I mean, at least W22. You need two derivatives of P, right?
Oh, well, believe so. Yeah. Believe so.
Right. Okay.
Believe so. Yeah. But also, when deriving all this stuff, it's assumed about double differentiation. Honestly, I didn't tell it before, but it's rather delicate stuff, you know. Especially, okay, I'll continue, Sasha. Yeah, so let's do some applications. Consider the traveling wave, yeah, and we'll have dispersion relation, whatever. We can express the frequency through the wave number. You can see that the system, as I promised you, has a cutoff frequency. It's here. It's also its approximation, of course, but it's small. So next, we can, of course, write down the a two-term asymptotic expansion of omega in terms of the small parameter epsilon. Epsilon is g to the 1/4. Well, and it was a dream of previous generation of structural people to get a right second-order term, second-order correction. Well, the first-order term, it's trivial, of course, but to get the correction right one, it was a pain, and it was many contradictory suggestions. Well, here I plotted the leading order and first-order approximation, and it's seen that the corrected approximation makes some sense. Well, again, I can correct the value of both phase and group velocities. Also, it was a desire. a desire of advanced engineers. And here I plotted the graph of both of them, and a crucial role belongs to the point of the intersection of in which the group velocity is equal to the phase velocity. Here, taking a refined expansion, I corrected the position of this point. The reason is that at this point, there is a resonance for a moving source, for a moving load. It's a very important point. It's called the critical speed of the moving load. It's very famous problem in structural dynamics, originated to Timoshenko. It was done somehow roughly in 1920, and a lot of efforts again were devoted to a correction of his result, but they were based on ad hoc arguments. Well, now let's speak about the degeneration. Here we have leading order dispersion relation for the leading order engineering model, which confirmed now, no criticism more with that respect. And it supports the scaling if G, the relative stiffness of the foundation, is small, yeah, the order of the frequency will be G to the half, and the order of the number K, it will be G to the 1/4. Yeah, it's trivial, of course, from here, but immediately we can see that when omega is close to the cutoff frequency, when the last two terms will cancel out each other, the K, the wave number, becomes to be much less than assumed originally. So there is degeneration of the original asymptotic scaling. We should do something different. And again, I have a right to criticize the engineering model because all the dynamics within that setup starts near the cutoff, yeah, near the cutoff. Below cutoff, there is no propagating wave. And immediately near the cutoff, the suggested model degenerates. So it doesn't govern a near surface behavior. And I will need absolutely different scaling, near cutoff scaling. I have no enough time to report on the details of asymptotic integration, which is similar within another scaling, but much more elaborated. Here we have no single equation for the transverse displacement W. You cannot split the transverse motion due to this Laplacian, yeah, and so on, with the tangential motion. U is the two-dimensional vector of tangential displacement. They are coupled now, and there are two equations. Here I presented two DC setup, more general than before, but it doesn't matter. We have a set of two equations. Yeah. In fact, three equations. I'm sorry again. We have a scalar equation 24 and a vector equation 25. Three equations instead of a single equation recommended by Kirchhoff and Winkler. And this equation supports a very interesting phenomena called veering point. Veering point. If you will write down the related dispersion relation, the associated one, and slightly simplify it, locally near this point, omega naught and k naught, we have such a shortened form of this relation. Delta is slightly amended small parameter, and you can see in the graph the varying of the dispersion curves. The bending dispersion curve, which was originally our aim, it was about the bending of a plate or beam supported by Winkler foundation. But we also see the effect of the extensional wave governed by the displacement vector u, and these dispersion curves do not intersect each other. We can observe the phenomena, as I said, it called veering. I'm sorry, veering. There is a comparison here of the exact result and asymptotic, and this veering takes place. So I'm returning back for two steps. Near the cutoff frequency, the bending wave of interest of the most practical value can be separated of the extensional wave, symmetric wave, which usually ignored, but it comes to the game near the cutoff. And finally, I listed here a few rather recent papers written mostly with my Turkish colleague Barış Erbas, and some time ago he was a PhD, about 20 years ago now in Manchester, supervised by Dave Abrahams, that now we are working closely, and he contributed a lot to this piece of work. Thank you very much for your attention. That's all for today.